All right, I will. I hope so. I think this is a little bit on, or is it just me? No? No, it's just me. All right, so let's kick this off. I'm going to talk about why everything is a stream and a little bit about quantum mechanics. So no high expectations, please. A little bit about me. I'm Christian. I wrote my first JavaScript in '97, so I'm really proud about that. I'm CEO and founder of a company called iTeam. I run something called Launch Hackers, which is really interesting for all of you to join. It's here in Scandic Grand Central every Wednesday. So it's a 4-year-long hackathon every Wednesday. And also organizer of Codopper. I'm really happy because I chose the right language, as most of you. So this is according to Stack Overflow. This is the most popular technologies that people want to work with. So that's super cool. The most dreaded ones are WordPress, SharePoint, CoffeeScript, which is good. A couple of years back, everyone was happy about CoffeeScript. I didn't like it, so that was good too. SQL Server and Objective-C, I hated those too, so that's fine. And a little bit about SQL Server is, of course, a good technology and everything is built on top of that, but I'm going to propose to you something else that actually can help a lot of problems that we usually solve with SQL Server and databases. So I hope that you're gonna follow what I'm going to say. So anyway, let's talk about functional reactive programming, or I would I try to summarize it in any way, and it's really hard because it's kind of a multifaceted tool. I would say it's a way to process streams of data, but only when someone is listening. And to me, the more I've been thinking about reactive programming, the more I've been thinking about this. Like, if a tree falls in the forest and no one's around to hear it, does it make a sound? And I'm going to prove to you that it doesn't. So. I have a theory that everything is based on streams, so I'm not biased at all. So this is a famous, the most famous experiment for quantum theory. It's called the double slit experiment. So if you point one laser or send some particle on top of two slits, it actually appears some sort of interference pattern in the background. But if you measure somewhere on the way, it actually changes. So that's really interesting, and I think that's an interesting way to kind of handle data. But if you aren't interested in measuring, nothing's actually happening, and when you measure in the end, something else happens. But to maybe explain this a little bit more concrete way, I'm going to switch to another example. So let's say that you are building your own Spotify or something. You have access to 24 million songs, and you have gotten the job to kind of actually put all of these files into catalog and to extract the metadata and extract the artwork and download all those files and maybe find the song if it's already in the database, or if it's not, just upsert or insert it into a database. This is kind of one job that would fit streaming data really well. And usually this would be done in some sort of sequential processing way. So you would start with reading the files from the hard drive and maybe start some sort of conversion job to convert all the files to MP3. And when that's done, you would extract the artwork, and then you would extract the metadata, and then would define the songs, and in the end, you update the database. And of course, if something happens in any of these cases, in the memory stops working or something else happens, you have to start over right from the start. So this is not a very suitable way if you want to be able to do this in a stable way. So the most of these times you would end up choosing something like a queue worker. Maybe you have RabbitMQ, or you have some other mechanism. But all of them are pretty much the same. You would push data into a queue, and the queue would be pretty exhausted pretty soon. You would just, start from read from the start, and then you would push things in front of you, and it's actually going to be a lot of memory, a lot of resources that would end up being used to do this. If you would choose some sort of stream pipeline instead, you can actually start controlling this flow a lot more. So instead of trying to kind of start with converting all the MP3 files, you would maybe start reading the songs and extracting metadata and store those in database and update the database. And maybe the rest of the conversion would be sorted based on popularity or something like that. So you could actually control which songs that you would actually put the effort to extract the artwork in the MP3s form. So this is probably a better way to solve it. And also, if you start with 24 million songs, you would probably come to a point where you actually get new batches. Maybe 500 new songs comes every week or every day or something, and then you would have to kind of handle that idea to both take the batch process and also stream process pipeline. So I'm going to show you a little bit how that's done. And also, one other thing that is really important to understand about streams is that it's actually not pushing; it's actually pulling. So instead of starting reading from the start with reading all the 24 million songs, you'd actually start from the end. So first thing would happen is that you go to the last point in the queue, start reading, calling the next function on that, which would call the next function on the previous step in the process, which will call the next function in the previous step, and in the end, it's actually starting reading from the database or from the file system. So this is the basic principle about streams. You're not actually pushing things. You're pulling them basically from the source, which gives a lot of interesting properties, which I'm going to go into a little bit more in detail. So, if you dive right into the code, this would be pretty much the overall idea about how to do this. So, either if you do it serial, you start from the start, you just find the songs in the database, you extract the artwork, you convert them to MP3, extract the metadata, and then you update the database. And if you want to do all of them in parallel, you would do something like that. You just start something which, as long as something happens from those merged streams, you would update the database. But let's talk about something else. Let's do a taxi dispatch system in JavaScript. And I am stupid, but I've already have 3 kids, so I'm fine. So if you look at this problem, and Taxi Stockholm is one of our clients, so we are working on this project. And this is also, I'm going to show you the code afterwards, and it's pretty cool. It's actually a pretty interesting way to solve this problem. But if you look at the problem of taxi dispatch, you would have some sort of state. You have some sort of positions from cars, which is a stream. You have some sort of bookings that is also some sort of stream. And then you would kind of have to send something out, some sort of dispatch to the car, and then some sort of send confirmation to the clients. So these are kind of the inputs and outputs from a system like this. But if you start by adding a little bit of more complexity, the nearest cars are not actually that easy to solve, because it's not always the same as closest ones. So if you have one car here and then one other car on the opposite side of the lake, you would probably not. Maybe it could be the closest car, but it's not the fastest car. If you have congestions, that's also the same. So this is a kind of complicated question to answer. What is the nearest car? You constantly get new updates for positions, so that's something that's constantly happening. And you get new bookings all the time, and you also want to be fair to drivers. So if you have one driver that actually has a lot of bookings the last hour, it's more convenient if you have the ability to choose. Maybe to dispatch this booking to another driver. It's not that actually it's the one that is nearest. So maybe you have some sort of some sort of area of acceptance from the user perspective, but where you can actually have other considerations from the driver's perspective. So this is kind of complicated, and when you start looking at it, it's like the flow of information goes all over the place. And if you would solve this problem with like SQL databases and views and stored procedures and everything, it's kind of hard to understand how you would model something like this. And especially if you want to be able to react on things, like one car that just dropped someone off just near here. Maybe that car is the best suit for this booking. And if you would take 1 minute or 2 minutes before you actually send the booking confirmation to the client, maybe that will help to kind of get more information into the decision. So this is kind of an interesting problem to see, so to test on this tool. So I actually did some sort of proof of concept on this, so let's try to do that. Let's talk about functional reactive programming. I've chosen between RxJS, Bacon.js, and Highland.js, and if any of you are interested in looking at this, you would definitely go for RxJS. Everything I'm going to show here tonight is based on Highland.js. And the reason for that is that when I started kind of testing these frameworks, RxJS had a very quirky way of casing all the methods. So it was taken from C#, and so all the method names were called in Pascal case. But I wanted so I chose Highland instead. But now RxJS have evolved, so now it's better, and now it looks exactly as it should. But I've stuck with Highland.js, so RxJS is one to choose. The interesting thing about JavaScript is that you can mix and match between different paradigms. So if you have functional mindset for some things, you can combine those with asynchronous mindset, but also object-oriented languages. So anyway, the problem: all the cars are moving every second. The traffic in the geography means that we have to look up every car according to the map, and every second counts. And the logic needs to be understandable, because if something goes wrong, the drivers, 4,500 drivers are knowing about the problems, and they are calling the customer service all the time. And it needs to be 100% uptime. We can't do any delivery or any production stops on Tech Stockholm. So this is actually the code that we ended up with. This is actually something that I'm pretty proud of, that is this readable. So you have the cars. You pipe that into the closest cars stream that would pipe the result of that. Take the first 50 cars. You pipe those into another promise that will look at the map and the real-time traffic situation and figure out which of these 50 cars that is actually the fastest ones, and take 5 of those and send those 5 cars into the next step of this process stream. So if you look at this problem from a normal perspective, you would do this by sending some sort of database, and you store procedures, and you split the logic all over the place, just because you have to leverage a lot of information stored in different places. But if you have all this information in memory, this is actually a much simpler problem to solve. So the only thing you need to do here is to have a stream of cars, and you have now a method that will take a stream of bookings and be able to stream those into these, combine those with these 2 different streams. This is a really interesting way of solving problems, and I'm going to show you a little bit more. The fastest cars, it's using some a database called OpenStreet database, OSRM, and the routing engine on top of that, which is stored in Docker. So you can actually query a lot of these queries locally on my machine. So to query 50 cars is actually something you could do within a second, which is really interesting. So this is the actual code that is running to do this. So the first line here is rate limits. So it says, like, I'm going to do 5 queries every half second. So that's the limit of queries I'm sending to dispatch And in the end, I'm sorting these on time to arrival. And this is the last step of this dispatch. So now it's using the stream of fastest cars that we just produced, and now it's filtering those on if the car is busy, and then it's sorting them on how many cars how many bookings this car has had the last hour, and then it sends an offer to this car, and if it's approved, that could be something that happens 1 minute or something like that afterwards. And then it actually sends the pickup confirmation to the driver. So this is code that we can actually talk to the client, and we can actually have a conversation about these rules with the drivers themselves, which is really interesting because you normally wouldn't be able to do that when you solve these kind of problems in a different way. And the most interesting property of this is that it's real time. So you don't have to do like any query every 10 seconds, or you have to like keep the one state stored somewhere. When something changes, new cars are available. So the data is flowing through these different pipelines in a particular way, and in the end, it ends up being one car dispatched to one booking. So presentation rule number 1: never live code on stage. I'm gonna do it with my blindfold. So let's see now. Before I run into the actual code, I'm gonna show it a little bit less complicated code. If we have a simplest program running Highland, would end up something like this. You have the query Highland, and this is the way that you normally use Highland in this sense. Highland is written by the same author that it was that wrote async, and also I think it was Lodash, or the other one, the underscore. And it uses pretty much the same principle. So you would definitely, if you're used to using Lodash or underscore, you would see the same syntax. So here we have an array of objects. That's the most simplest stream we can find. We take a batch of 2, and we console log each batch we get, and then we write how many items we have consumed. So down here we can see the result. So in the first batch we have foo, and then we have bar and foo, and we have herp derp. Here if we would do something interesting, if we remove the last line here and we rerun the code, what will happen? Nothing, because nothing is actually requesting the information. So this is the first thing you need to know about functional reactive programming, that it's actually not pushing things forward, it's actually dragging things downwards. So if you have a pipeline of things and nothing's working, that usually means that you have not started to ask for any information in the bottom of the page. So this command each here is actually starting to ask for, and it's starting consuming this stream. And here we can do, of course, we can do something like this. So now we are only interested in things that have a property called foo. And without the batch. And we get one value. So in the normal way of like all the things that you would normally use from some sort of Lodash or underscore, any library that you would use in normal way, you could use in this as well. So there's a lot of different methods. I'm not going to go into all of them if you don't want me to. So But I'm gonna show a little bit more advanced example just now. So let's go into the songs. So let's say we have no, sorry. Not gonna show you that really right now. So this is the stream, but instead of using an array of items in this, we could convert this into real stream that would actually produce new values all the time. And if we do it like this, so this is the most basic example of a stream. You have something called a function that we called with two parameters, one push and one next. So push you can use to either push some sort of error, or you could push a value. So let's say we push 1, and then we say that we are finished with this batch. And instead of our array, we take the stream instead. And now we get a constant stream of ones. That's really boring, so we change that to math.random, so we can see the actual change. And I need to save it before I restart it. So now we have exhausted our stream with a lot of data. And again, if we don't have the each in the bottom, that is actually not gonna do anything at all. So it's the each that consumes the string that actually runs the function, the next function that would end up with one value that is coming from the push stream. So this is the function that ends up running all the time, whenever it reaches the next. So here we have no. Yeah. So let's say that we wanna do something about the stream. Let's say that we're gonna do a reduce on this stream. And then we do A, B. Does anyone know what's gonna happen now? Yes. No, it's actually that. Yeah. What? Yeah. This is a quirky way. Reduce in Highland, for some reason, have not used the proper way of using the memo. So the memo, the initial value that it's going to start with, is actually the first parameter, and that's very quirky. So exactly, now it just continues, and it adds up in memory a value that it actually show. So that's something good to know about streams, that since they are endless, you can't really apply exactly the same methods that we would use when using normal array manipulations. You would rather use the scan method. It actually takes the value, reduces the value, but also emits the result of that into the stream. So if when we run this, it's oh, never live code. Mistake. No. Scan. Scan 1, yes. Thank you. No. number? Aha. Yeah, that's very clever indeed. 1. Let's do not multiply. Let's do plus instead. Yay! So now it's actually working. So streams have different properties than the usual array manipulations, and this is a really powerful tool when you have some sort of access to things that are stream-like. So if you're gonna solve some sort of problem where you have when you have event emitters, you have promises, you have arrays, or you have files, or you have requests, anywhere where you actually have some sort of stream of data, you can start using these kind of tools to not only use it for JavaScript on the client side, where you can use a lot of different magical things as well, like use it to make drag and drop and things like that much easier. But also for using to do more complicated things on the server. So if you look at another interesting thing is that you can use this to run promises. So right now we only use values that we already know the value to, but that are synchronous. But if you want to run asynchronous code, we actually can do that as well. So if we use a promise here with that just runs that timeout, so we can instead of just sending these directly, we can do a map of a promise. So let's do value, and we do wait, and we say 1 second, and then we're gonna emit the value. We see that we now have a long list of yeah, exactly. So when I do this, I actually take my original stream and I send those to my promise, and the promise is directly emitted, right? So at this point everything is still synchronous. But if I want to actually be able to do something and wait with the flow until we have resolved our value, I do something called flatten. So now I have maps, I have my promises, and I've sent those to on the stream. But instead of just sending them to console, we actually wait for them and flatten those and resolve those promises. And one thing you need to do then is to actually convert that into a stream. So this is a way to by adding this underscore, we are converting a promise into a stream. So when I run this now, I'm actually gonna get one new value for every second. So this is a very interesting way of sending something as a promise, and when the promise returns, we get the rest of the value. So now we're not over-exhausting our memory and our bandwidth or anything like that. We just take one value, send it off to a promise, and when that resolves, we continue with our flow. And nothing else is consumed from the stream. So as you can see, this push function will never run more than this amount of times that we do here. So if we add some sort of console log here, we say hit here, we're gonna see that it's not like adding a long list of array with array in the beginning and pushes those to the next part. Save, thank you. So now we're gonna get 1 hit, 2 hits, 3 hits, 4 hits. So this is the magical property of using functional reactive programming in my world. It's like you define your pipeline of things that are going to happen after each other to to parse your data that comes in your stream, but you never asks for more than you can handle. All right. So here's a little bit more advanced example. So now I have used the same idea. We have a stream called songs that is exactly the same as before. So we have a push function, an X function. The push pushes null as an error, and then an object. And this is used as faker, which is a great library if you want to fake data. So this will fake an ID, a name, an artist, product adjective, which was a good idea for faking title of an album, and then it returns a sample or URL with like random images on the internet, and then a product name again for the title. And if we just run this without any magic. We should be able to see all the random songs that have an artist name. Just need to change this into songs. So here is the magical weird song names based on fake data. The intelligent concrete sausages performed by the artist called Charlie Gutwigsy Jr. And the title of the album is fantastic, rustic, etc. So this is a really easy way to kind of also to produce a lot of data. And the interesting thing when starting looking at data in this way is that you can switch between an array, like we did, and a stream of data. And you can combine them. You can take one batch of data and you can combine those with real-time data. So you can optimize your flow to actually take all the 24 million songs in the beginning, but you can merge those with a stream of new songs that comes in from somewhere else. And the rest of the pipeline is actually going to be exactly the same. So by doing this trick to convert everything to one interface and start using these kind of methods to transpose your data into new things, it's actually really interesting. And if you have something that contains a URL, like in this case, so I now have download album art, which basically just takes fetch. So it downloads from the internet this image and then takes that stream, and right now it just ignores everything except for the status. So we should be able to see that it's status 200 OK. And as before, we want to flatten those, so we actually not get the promise, but actually get the library, the information. And I need to save before I do something. I'm going to stop this right away, because otherwise Google's network going to be over-exhausted, because I haven't added any rate limit. So now I just take the fake images and I get the URLs, and so this is the URL, the cats, and I'm downloading that. So now I actually have a promise that is resolved. It's downloading this URL, and it adds that URL and the stream into this object. And if I wanna be nice to my network provider, and also of course the source of this wonderful lorem people, I also apply a rate limit. So this is also a very good way of controlling. So if you have a really huge base of data, you have a database in your production environment or something like that, you don't want to push things too hard on that server. This is a really good way of controlling this flow. So you don't have to download everything first and over-exhaust everything, and then you still end up maybe saving it somewhere, and it doesn't matter. So by doing this, you control the whole flow from the first read of the first file and into the last step, where it actually controls how fast it's going to read in the first place. So now I'm controlling this to one one song per second, which is really nice. And if I want to, I can also add a batch to say, okay, so I'm interested to get 10 of these in a batch, and then I'm gonna do a rate limit on that. So now I'm gonna actually do a batch of 10 that is gonna run in parallel to the server, and then do that every second. Because a lot of times you have one very big file that's really long, that takes forever to download, and you don't want to have that file to kind of stop the whole flow. So by doing this, you actually can control how many of your steps are going to be run in batch. So now I'm doing, yeah, so now I'm getting chunks of data. So 10, 10, 10. That's really interesting. And damn it. So the last step is actually for me to dare to start running this in development mode, this dispatch engine, to see if it's working. How is it with time? Is it okay? Okay. No idea. That's good. We can continue on forever. So this is really interesting. So now we have cars on the map, and hopefully these are gonna move after a while. So now this actually fetches the positions from one place every 10 seconds, and it sends those over the wire to the screen. And hopefully yeah. And it's also interesting that now, even if I just get the positions every 10 seconds, so now I'm here and now I'm here, I can send that off to my OpenStreet routing engine. So, and to calculate the best possible way, the most probable way for this car to actually move on the street. So, in this car here, it's actually it's really hard to know in the beginning when you get the first position if it's actually on that road or if it's somewhere else, because it can as well be on the bridge on top of the road. So you don't know for the actual first ride. But and as you can see, this is not perfect. And in test mode now, I'm actually not even using the real data. Into congestion, because you get new positions all the time, and as you can see now, it's quite weird. But when you get new positions, you know how far was it from the previous segment of the road into the next segment, which means you can calculate what's the actual speed of that segment of the road. So when you get two positions that are really far away, you can calculate for each of those segments in that between those positions. You can calculate how far and how fast it's actually on that position right now. And this is actually not things that we have done. It's just using open source, this OpenStreet routing manager. So it's a Docker instance. You just start running it, and it continues to do this for you. So that's really interesting. And of course, Google have similar services, so it would be really easy to use those services as well. But if you want to do this really, really often, and you don't want to hit the limits of Google to kind of calculate all these positions and do all these things, so it's really good to use Google for a lot of things as well, especially when you get the live real-time data for traffic in the future. So how long it's going to take for tomorrow morning go from Arlanda to Sollentuna or something like that, then Google has a lot of history data to use that. And if you look at the code for this, it's actually the same thing. It's really it's quite easy to follow, I think, at least. Yes. So here's the car. So when we update position, we match the positions to the map. Go to position here. This is the code. So it matches the position on the database and then calculates the same thing backwards. Yeah. and this is the car finder in its whole. So you have closest car, fastest cars, and the pipeline that uses both of them in the same pipeline. All right, that was it. Yeah. Oh, sorry. Hey.
Is it now on? Okay. Weird. we could discuss the UX. Okay. So you call these pool-based models, but I'm thinking about the times that I read about functional reactive programming and my experience with reactive extensions. And normally we have a stream or an observable, and you subscribe to the observable, and the observable pushes it feels like it pushes data at you that you are observing it.
Yeah, exactly, and that's exactly how it feels.
Okay.
It's really hard to write this code backwards. So you would never write the code like from the bottom up. So you always write the code in that way. You start with and as you see it, like the example I showed, it seems like it's pushing in front of you, like this one here. This, especially since the name of the function is push, you think that you're pushing things, but what you actually are doing is that you're telling the framework that this is the function that you're going to run whenever you need the next the next value in this stream. And we have used this for doing like getting history data. In our test environment we have in Tax Stockholm we use 1 week late data. So I actually have an example of that as well. So here we have a streamer that you can use whenever you want to have access to bookings from the production data, but 1 week old. You get like very good example data that is coming from 1 week exactly at this point in time for last week, but it's actually just using the history and uses these push and next functions to say that now I'm pushing things from the history, and then I wait so many seconds it takes from the last booking to the next booking 1 week ago, and then I push the next data. So this is a really good way to actually simulate your production data in just a few lines of code. So you write it as you would push things, but what it's actually doing in the background is that it's actually pulling things and goes to kind of the source of data, and then it evaluates that function, and then all the functions that comes afterwards is going to be resolved in that order.
So inside the implementation of each of these functions, there's something calling on next. But then from the point of view of the consumer, that is the observer, I would feel like something is being pushed at you, right?
Yeah, I don't really follow. Sorry.
Because it's just, I always thought about reactive programming as something that pushes data at you. But you mentioned that you call it like it was pulling, like when you call an iterator, like give me the next element, give me the next element.
Yep.
But in this case, it's more like you have a callback, and then when the stream has data available, it gives you data without you needing to ask for it explicitly. Right?
Yeah, no, I understand. Yeah, sure. Yeah, absolutely. There's different, and that would be the event emitter pattern. So you can't really control if something happens. If the user clicks the button, it actually sends the data. So yeah, you have those streams as well, where you actually push things and you can't control them, and then you just need to react on them. But and what is happening in those cases is that you have some sort of data where you start pushing data, like starting to build up something. All of those events gets queued into memory in the background in framework. So for the rest of the pipeline is going to be exactly the same. But it's going to use, first of all, it's going to use the buffer, and after a while it's going to end up in having nothing. And then it's going to listen to the next event. And as soon as that event comes, then it's going to push that. So all of these frameworks and RxJS and other frameworks as well, they have a similar feature. So whenever you have something, you have an internal buffer that takes care of that extra data that you haven't used in it. So absolutely, you don't necessarily just magically just removes all the data. It's getting stored in the background. But usually, if you have the ability to keep the back pressure intact, you definitely you can do that. And in Highland you have the option to either fork a stream or to observe a stream. So if you observe a stream, you can't really control what's going to happen, and that's exactly like you mentioned, that you can't really control if it's going to read more from the source or not. But if you fork it, you actually have a stream, and you can fork that into a separate stream, and both of them control the pace that the source is going to be read. So it's a little bit. It takes a while before you are getting used to kind of these different concepts. But it's when you start thinking in this way, everything is actually really interesting.
Yeah, like everything becomes a stream. Right?
Yes, that's the title of the talk. Any other questions? Thank you. All right.